Now, since the first method, which is deadlock prevention, does not lead to great results in a way that it can cause low resource utilization and possible starvation, then let's discover a second method to prevent deadlocks, which is deadlock avoidance. So with deadlock avoidance, we want to require we will need that the system has some prior knowledge about the resources available, and each thread will need to declare the for instance the maximum number of resources of each type that it may end up using. And the deadlock avoidance algorithm will dynamically examine the resource allocation state in the system and make sure that there will never be a circular wait condition. And then the system can decide for each request whether or not the thread should wait in order to avoid a possible future deadlock, right? So it will only consider the resources currently available, and it will also consider the resources currently allocated to each thread, as well as the future resources that are going to be released by each thread in the future. So with deadlock avoidance, we're talking about the safe state of the system. So when a thread requests an available resource, then the system have to decide if the immediate allocation of that resource will leave the system in a safe state. Now, safe state means if the system can allocate resources to each thread in some sort of an order and still avoid a deadlock. So the rule here is if a system is in a safe state, which is the gray area right here, then there is no deadlocks for sure. Now, if the system is an unsafe state, which is the blue area right here, then there is a possibility of a deadlock. So we do not want to, we want to make sure that the system will never actually enter that blue area, will never enter the unsafe state. So we say that a system is in a safe state if it does exist such a sequence, right, of threads T1 to Tn, such that for each thread T1, the resources that it still can request can be satisfied, which means the system can allocate those resources, right, using the currently available plus the resources held by other threads. Of course, maintaining that j is less than I. So it's kind of an order of execution of the threads. So we're trying to execute the threads in some sort of order that will prevent deadlocks from happening, that will maintain a safe state in the system. How can we do that? So to explain more, if the thread ti it needs the resources that it needs, they're not currently immediately available, we can put it to wait until tj, which is the previous one, has finished and released those resources. So it's kind of the threads are coming in orders, they're using resources, they're done, they release them. Then the next one will execute because now we have more resources because the first one released the resources that it was holding. So we're trying to maintain this order of execution, okay? So once TJ is finished, TI can obtain whatever resources that it needs, then execute, then release and return those allocated resources that it was holding, then terminate. So when Ti terminates, then Ti plus 1, the next one can again obtain whatever resources it's needed and execute and terminate and so on and so forth. So when no such sequence exists, we tried to apply the algorithm and we did not find this order. We couldn't find the sequence T1 to Tn that will maintain a safe state. If we couldn't, then we say that a system is in unsafe state. So this is how we are testing, safe versus unsafe. So safe means that there exists an ordered sequence T1 to Tn that maintains a safe state. We still don't know how can we do that ordering. And that's what the main algorithm is about. How can we create this ordered sequence? Now, there is two scenarios. Either we do have just one single instance of a resource type. In that case, to do the deadlock avoidance, we use the resource allocation graph method, or we have multiple instances. In that case, we use a algorithm for deadlock avoidance that's called the banker's algorithm. So in case we have just one instance, we use the resource allocation graph. So here we define a new type of edge that is called the claim edge. So T2 from R2, this claim edge means that the thread T2 may request the resource R2, right, in the future. Now this claim edge will convert into a request edge when the thread actually requests the resource. And then the request edge will be converted into an assignment edge when the resource is actually allocated to the thread. And then when a resource is released by the thread, the assignment edge converts again to a possible claim edge. And so a claim edge can be converted into an actual request edge only if the assignment edge will not leave the system in an unsafe state, which means it will not result in creating a cycle in our resource allocation graph. So suppose Ti requests a resource Rj. If we converted that into an assignment edge, then we have to check if we ended up forming a circle in our graph. So if no cycle exists, then the allocation will leave the system in a safe state, so it is allowed. But if we ended up in forming a cycle, then this allocation will put the system in an unsafe state, and we want to avoid that. In that case, that thread will have to wait for its request to be satisfied, so it cannot be immediately allocated that resource. So for example, if we start with this resource allocation graph, so you can see that P1 is requesting R2 and P3 is also requesting R2, right? So we're going to assume that we assigned a resource R2 to process P1, okay? So here we did not actually allocate the resource yet, we're just assuming, okay? What if we did allocate resource R2 to P1? So this request edge will be changed to an assignment edge, okay? So what do you notice here? What happened? We have a directed cycle in our resource allocation graph, which means possibly this will put us in an unsafe state where a deadlock may happen, okay? Now, on the other hand, assume that we did assign, again, we're just assuming that we did assign resource R2 to the process P3. Then we check, do we have a directed cycle? Let's see. There we go. It's not a directed cycle. So this assignment edge will not leave us in an unsafe state. So it is safe to actually proceed and assign this resource to P3. So we said that when we have multiple instances of resources, then we use an algorithm to avoid deadlock that is called the banker's algorithm. The idea is that each thread has to provide the maximum use that it will end up using, and then of each resource type. And then when a thread requests a resource, depending on the state of the system that we will end up with, sometimes it may have to wait. And then when the thread is done using the resources, it has to return them all in a finite amount of time. So to start applying the banker's algorithm, we're going to define some data structures that we're going to use in the algorithm. The first data structure is available, which defines the number of instances of each resource type that we have available in the system. Max data structure represent the maximum need or the maximum need of a process. So for instance, we can say that process Ti may request at most a maximum of k instances of resource type Rj. And then allocation represents the current current allocation to a process. So how many instances of a resource type are currently allocated to a process. And then need equals to the maximum allocation that process may request minus the current allocation that process is currently holding. Okay, so let's assume this is our system and we currently have 3 resource types, A, B, and C. And so we have one process P1 that is requesting 1 instance of A, 0 instances of B, and 2 instances of C. So this is the current allocation of each process in the system. This is the maximum allocation that each process may request, and this is the number of currently available resources of each type that we have in the system. And so the first thing we start doing, so we'll explain the banker's algorithm with an example, and then you can take a look at the algorithm pseudocode in the notes provided. So the first step we have to do is to calculate the need for each one of these processes. And we said that the need is defined as the maximum minus the current allocation. So need means how much more resources this process still needs. Therefore, for P0, we're going to have the maximum allocation, which is 753 minus the current allocation, which is 0, 1, 0. So P0 still needs 7, 4, and 3. And then same thing for P1. It's the maximum, so 322 minus the allocation, which is 200. So P1 still needs 1, 2, 2. Same thing for P2, it's 902 minus 302. And so it's 6, 0, and 0. P3, it's the maximum 222 minus the current allocation 211. So it still needs 0, 1, 1. For P4, it's 433 minus 002. Therefore, it's 431. And so once we calculated the content of the need data structure, then the steps to apply this algorithm are the following. So step number 1 is we have to check if the request is less than the need for that process. So the request was 102 and the current need for process P1 is 122. So it is indeed less than the current need. And then the second step is to check that the request is less than what we have currently available in the system, which is 332. It is indeed less than the current available resources. And then step number 3 is to update the available and allocation and need data structure. So the available will be equal to the current available minus this new request by P1. So the idea is we want to assume that we did grant P1 what it's requested. So we will update accordingly these data structures, and then we will check, are we going to end up in a safe state? So if yes, then we will grant P1 this request. If we will end up in an unsafe state, then P1 will have to wait. So let's update these data structures. So available now will be equal to 332, which is the currently available, minus the new request, which is 102. So if we assume that we did grant this request, we will end up with an total of 230 available in the system, and the allocation of P1 will be equal to the current allocation plus what we just granted it. So it is 2 plus 1, 3, 0 plus 0, still 0, and then 0 plus 2, 2. And then the need will be the current need minus the request. So 1 minus 1, 0, 2 minus 0, 2, and then 2 minus 2 minus 0 is 2, and then 2 minus 2 is 0. So once we updated these data structure, as we said, step number 4 is to apply the safety algorithm. So it's called the safety algorithm to mainly check, are we going to end up in a safe state or no? And so let's try and apply the safety algorithm here. Again, the pseudocode is provided in the notes. So the idea is to try and go through the different processes, and based on their needs and the current available resources, we will check which process can we service first. So we ask ourselves, can we service P0? So P0 currently needs 7 instances of A, 4 instances of B, and 3 instances of C. But we only have 2 instances of A and 3 instances of B and 0 instances of C. So this is what we have available. So we cannot service P0 yet. Next, can we service P1? So P1 still needs 0 of A, 2 of B, and 0 of C. So yes, it is less than what we have available, so we can start with P1. So if we service P1, then we will have to update the currently available resources to be equal to what we have currently, which is 230 plus the current allocation of P1, because we said one of the rules is that if we grant access to those resources to that process, then once it's finished, we'll have to put down and return those resources to the system. So then if this is done, then we will end up with the current resources plus 320 that was held and released by P1 when it's done, and therefore the current available resources are 5 are 5, 3, 2. So we initially start with assigning the false. So we ask ourselves, is this process done? Okay, so initially they are all false, and then once we service one of the processes successfully, for instance P1 here, it's going to turn into the state of true. Okay, so then this is gone. So we ask the same question about P2. We cannot yet service P2 because it's asking for 6 instances of A, which we do not have available yet. Now we ask, can we do P3? P3 is requesting 0 of A, 1 of B, and 1 of C. So yes, we do have that available in the system. So we can actually, P3, we can actually service P3, and then we will end up with the current allocation of P3 plus what we already have available. So 532 plus 211, and this is equal to 743. And P3 is gone, and we turn its state to true, which means it's done. Now can we do P4? So it's requesting 4 of A, 3 of B, and 1 of C. Yes, we can do that. So P4 is next in the sequence. And then we're going to end up with 743 plus what was held by P4, which is 002. And this is equal to 745. So P4 is gone and its state turns to true. And then we go back up again to P0. P0 called requested 7 of A, 4 of B, and 3 of C. So now, yes, we can service P0 next. And we're going to end up with 745 plus 010. And this is equal to 7, 5, right, and 5. So P0 is gone, and we turn its done state to true. And lastly, P2, it's requesting 600. We do have that in the system. So P2 is next, and then we're going to end up with 755 plus 320, which is 10 instances of A and 5 instances of B and 7 instances of C. And this process is done, and we set the state of true. So the last thing we're going to do to determine the state of the system is to check this state data structure. If all of them are set to true, then we say yes, this system will end up in a safe state, and we call this the safe sequence. Okay, and then we do grant this request to P1. Now, if at least one of these processes state ended up with a false value, then it will not be a safe state, it will be an unsafe state, and we will not grant this request to P1, and it will have to wait. So this is what the banker's algorithm is about. So we have 4 steps. Step number 1, we check that the request is less than the need. Step number 2, we check that the request is less than the currently available. Step number 3, we're gonna pretend and assume that we did assign that request to that process, and we're gonna update these data structures accordingly. And then we're gonna apply the safety algorithm to determine the state of the system that we will end up with. Okay, so let's stay with the same system example, and now let's assume that we have a process T4 or thread T4 currently requesting 3 instances of A, 3 of B, and 0 of C. So again, let's apply the banker's algorithm. So first thing is checking if this request is less than what that process needs. So this is the need 431. Yes, it is less than the need. The second thing, we're going to check if it's less than the currently available. which is not. Therefore, it's not going to be granted immediately. Now let's assume that we have a new request from T0 to hold 0 instances of A, and it's requesting 2 instances of B and 0 instances of C. So again, we check, is the request less than need? Yes, it is. Is the request less than what we have available? Yes, it is. So we have to update the we're going to assume that we did grant T0 access to this request. So we're going to update the current allocation to be 0, 3, and 0. And then the need will be 7, 2, 3, right? And then the current available will be 2, 1, 2, 1, 0. Okay, and then we will try to apply the safety algorithm to determine if we will end up in a safe state. So let's see. Can we service T0? We can't, because the need is more than what we have available. Can we service T1? 0, 2, 0. No, we can't, because it's requesting more than what we have of B. Can we service T2? It's requesting 6 of A, but we only have 2 of A. Next, can we do T3? We can't, because it's asking for 1 of C and we only have 0 of C. Can we do T4? Nope, it needs more than what we have available. Therefore, we check also initially all of their states was false, and we couldn't service any of them, and so we're gonna end up at the end with all of these thread states to be false. Therefore, we are in we will end up eventually in an unsafe state, and therefore we cannot grant the T0 access to this request immediately, and it will have to wait.